Good morning, everyone. We are Group 2, and we are here to present to you the following.
In this problem, we are asked to formulate a shear and moment equation, and using this, we have to draw the shear and moment diagram. So, we have here an overhanging beam. The first step to draw the shear and moment diagram is to step 1. Find the support reaction. By summing up moment at D, we can find reaction at B. So, summation of moment at D is equal to 0 wherein clockwise direction is positive. Positive RB multiplied by moment arm of 6 minus force A, which is 600, multiplied by moment arm of 7.5 minus force C, which is 800, multiplied by moment arm of 3 minus the moment of the uniformly distributed load, which is represented by resultant force, which is 2000, multiplied by the length of action, which is 7.5, multiplied by moment arm of 7.5 over 2, since we know that the resultant acts at the middle of its length of action, plus the resultant of another uniformly distributed load, which is 3000, multiplied by 2, multiplied by moment arm of 2 over 2. So, we have our reaction at B that is equal to 9,525 Newton. Now that we have reaction at B, we can now compute for the reaction at D by using the summation of forces along the vertical axis wherein upward is positive. Positive RB plus RD minus 600 minus 800 multiplied by 3 minus 2000 multiplied by 7.5 minus 3000 multiplied by 2. Now we have reaction at D that is equal to 12,875 Newton. And now that we are done in step 1, we can now proceed to step 2. Analyze per span. So in order to analyze span AB, we need to make a section plane between span A and B. After that, we can now formulate an equation for shear or V and moment or M of span AB. Now let us analyze the span AB. Let us put this section plane and isolate the left side. We will have this figure. As you can see, there is still 600 Newton downward load, and here is the section plane, and there is an X, which is the distance from the left edge. Due to imbalance, the fibers in our beam will have resisting shear and moment. For shear AB, we have V is equal to summation of vertical forces considering the forces at the left side of our section plane. So we have negative 600 minus 2000 multiplied by X. Moment at AB, we have M is equal to the summation of moment considering the loads at the left side of our section plane. We have a negative 600 multiplied by X minus 2000 multiplied by X multiplied by X over 2. Now, let us simplify. We have negative 600 multiplied by X minus 1000 multiplied by X squared. After that, we can now move on our section plane between span B and C. By doing so, we can now formulate an equation for shear and moment of span BC. Let us now analyze span BC. Due to imbalance, the fibers in our beam will have resisting shear and moment. For shear BC, we have V is equal to the summation of vertical forces considering the loads and force at the left side of our section plane. So, we have negative 600 plus 9,525 minus 2,000 multiplied by X. So, let us simplify. We have 8,925 minus 2,000 multiplied by X. Now for the moment at BC, we have M is equal to the summation of moment considering the loads at the left side of our section plane. So if we simplify it, we will now have negative 14,287.5 plus 8,925 multiplied by x minus 1000 multiplied by x squared. We can now move our section plane between span C and D. Due to imbalance, the fibers in our beam will have resisting shear and moment. For shear CD, we have the summation of vertical forces considering the loads and forces at the left side of our section plane. Now we have negative 600 plus 9,525 minus 800 minus 2,000 multiplied by x. So if simplify it, we will now have 8,125 minus 2,000 multiplied by x. Moment at CD, we will have m is equal to the summation of moment considering the loads at the left side of our section plane. To simplify it, we will now have 8,125 multiplied by x minus 10,687.5 minus 1,000 multiplied by x squared. Now let us analyze span DE. Due to imbalance, the fibers in our beam will have resisting shear and moment. For shear DE, we have V is equal to summation of vertical forces considering the loads of forces at the left side of our section plane. So if we're gonna simplify it, we will have 28,500 minus 3,000 multiplied by x. Moment at BE, we will have m is equal to the summation of moment considering the loads at the left side of our section plane. If we simplify it, we will now have negative 1,500 multiplied by x squared plus 28,500 minus 135,375. After this step 2, we can now proceed to step 3. Draw the shear diagram. We will now having shear diagrams by using shear equations. Let's start with span AB. First, we will be using this shear equation. Shear at AB is equal to negative 600 minus 2000x. At point A, where x is equal to 0, by substituting the value of x in this equation, we got negative 600 Newton as the shear at point A. Since we got a negative value, we will be putting it under a reference line. Next, at point B, wherein x is equal to 1.5. By substituting the value of this to the equation, we got negative 3,600 Newton as the shear at point B. Since we got a negative value, we will be putting it under our reference line. Now with span BC, we will be now using the equation shear at BC is equal to 8,925 minus 2,000 multiplied by x. At point B, where x is equal to 1.5, by substituting it to this equation, we got 5,925 Newton as the shear at point B. Since we got a positive value, we will be putting it above our reference line. Next, now at point C, wherein x is equal to 4.5. By substituting the value of x to this equation, we got negative 75 Newton as the shear point at C. Since we got a negative value, we will be putting it under a reference line. Now with span CD, we will be using the shear equation. Shear at CD is equal to 8,125 minus 2,000 multiplied by x. At point C, wherein x is equal to 4.5. By substituting the value of x to this equation, we got negative 875 Newton. Since we got a negative value, we will be putting it under our reference line. Next point at D, wherein x is equal to 7.5. By substituting the value of x to this equation, we got a negative 6,875 Newton as a value of shear at point D. Since we got a negative value, we will be putting it under our reference line. Now, for span DE, we will be using this shear equation. Shear at DE is equal to 28,500 minus 3,000 multiplied by x. At point D, wherein x is equal to 7.5. By substituting the value of x to this equation, we got 6,000 Newton as the shear at point D. Since we got a positive value, we will be putting it above our reference line. Now, at point E, wherein x is equal to 9.5, by substituting the value of x to the equation, we got a 0 Newton as the shear point. Since we got a value of 0, we will be putting it in line with our reference point. And now, this is the shear diagram for this beam.
Now that we are done drawing our shear diagram by using shear equations, we can now proceed at step 4, which is to draw our moment diagram by using moment equations. First, let's start with span AB. For span AB, we will be using this moment equation. Moment at AB is equal to negative 600x minus 1000x squared. At point A, where x is equal to 0, by substituting the value of x to this moment equation, we get 0 Newton meter as the moment at point A. Since we don't have any support here at this point, therefore our moment is 0. Next, at point B, where x is equal to 1.5 meter, by substituting the value of x to this moment equation, we get negative 3,150 Newton meter. Since we have a negative moment, therefore we have to plot it below our reference line. As you can notice, our moment diagram is in frowning curvature since our shear diagram is increasing at the negative side. Now for our span BC, we will be using this moment equation. Moment at BC is equal to negative 14,287.5 plus 8,925x minus 1,000x squared. At point B, where x is equal to 1.5 meter, by substituting the value of x to this moment equation, we get negative 3,150 Newton meter, which is also the same with the moment we have computed from the previous equation because they are at the same location, which is at point B. Therefore, this negative 3,150 Newton meter will remain at this point. After taking the moment at P, we will not go directly at point C because there is still an internal shear at this point, which is equal to 0. So to compute for the moment at this point, we need to find first its location, which will be denoted as x. In this case, this point is located within the span BC. Therefore, we will be using the shear equation from span BC, which is equal to 8,925 minus 2,000x. Computing for the value of x, we get 4.4625 meter. Therefore, the location of this point is equal to 4.4625 meter from the point A. So we can now compute for the moment at this point by using the value we have computed for x. By substituting the value of x to this moment equation, we get 5,626.41 Newton meter. Since we have a positive moment, we have to plot it above our reference line. Now at point C, where x is equal to 4.5 meter, by substituting the value of x to this moment equation, we get 5,625 Newton meter. So we can now plot it here. Now for our span CD, we will be using this moment equation. moment at CD is equal to 8,125x minus 10,687.5 minus 1,000x squared. At point C, where x is equal to 4.5 meter, by substituting the value of x to this moment equation, we get 5,625 Newton meter, which is also the same with the moment we have computed a while ago. Therefore, we will not be moving this point. Next, at point D, where x is equal to 7.5 meter, by substituting the value of x to this moment equation, we get negative 6,000 Newton meter. Since we have a negative moment here, that's why we will be plotting it below our reference line. Now for our span DE, we will be using this moment equation, negative 1,500x squared plus 28,500x minus 135,375. At point D, where x is equal to 7.5 meter, by substituting the value of x to this equation, we get negative 6,000 Newton meter, which is also the same with this one. Last, at point E, which is at the end of our beam, where x is equal to 9.5 meter from point A. By substituting the value of x to this moment equation, we get 0 Newton meter. Therefore, our moment diagram will be back at 0. Now we are done with showing our shear diagram and moment diagram by using shear equations and moment equations.
After we draw the shear and moment diagram of the particular problem, we will sketch the expected deformation of the beam. So, before we sketch the deformation of the beam, our first thing to do is to isolate the moment diagram. And then, after that, we will project the point from A to E. Next step, we will draw our support, a roller at point B, and a pin at point D. And before we sketch the diagram, we will refer to the figure here. When our moment is positive, a beam bends concave upward like smiling. And if our moment is negative, a beam bends concave downward like frowning. So our span A to B have negative moment. So our bending moment is concave downward like frowning. So our span B to C, we have a moment of positive, so that our bending moment is concave upward like smiling. To our span C to D have positive moment, so that our bending moment also is concave upward like smiling. To our span DE have negative moment, so that our bending moment is concave downward like frowning. So through this diagram, we will see or locate the behavior of deformation of our beam due to the loading of the point A to E. So, we will call this diagram as deflection diagram.
So now we will proceed to the shear diagram shortcut method. So first we need to find the support reaction at B and D, and we will use the summation of moment at D is equal to 0, and we will come up to the solution of reaction at B multiplied by 6 minus 600 multiplied by 7.5 minus 800 times 3 minus 2000 multiplied by 7.5 times 7.5 over 2 plus 3000 times 2 multiplied by 1 is equal to 0, and the reaction at B is equal to 9,525 Newton. And for the summation of vertical forces is equal to 0, we will come up to the solution of reaction at B plus reaction at D minus 600 minus 800 minus 2000 multiplied by 7.5 minus 3000 multiplied by 2 is equal to 0, and the reaction at D is equal to 12,875 Newton. After getting the support reaction, you can now proceed to drawing the shear diagram, but before that, we need to find the area in each segment or span. And for area 1 or from span AB, area 1 is equal to 2000 Newton per meter multiplied by 1.5 meter is equal to 3000 Newton. And for area 2 from span BC, area 2 is equal to 2000 Newton per meter multiplied by 3 meter is equal to 6000 Newton. And for area 3 from span CD, area 3 is equal to 2000 Newton meter multiplied by 3 is equal to 6000 Newton. And for area 4 from span DE, area 4 is equal to 3000 Newton per meter multiplied by 2 meter is equal to 6000 Newton. After finding the area in each segment, we can now proceed in drawing the shear diagram. As we can see in point A, there is a 600 Newton load downward. So from 0, we will go down to negative 600 Newton. Then after, we are going to add the area 1. So negative 600 Newton plus negative 3000 Newton is equal to negative 3600 Newton, and that will be go downward to B. And at point B, there is a reaction load of 9525 Newton. So we will add that to negative 3600 Newton, and that will give us 5925 Newton, and that is going up. Then next, 5925 Newton plus area 2, which is negative 6000 Newton, and that will be negative 75 Newton downward going to C. And at point C, we have again a load of 800 Newton downward. So, negative 800 Newton plus negative 75 Newton is equal to negative 875 Newton downward to C. Then, add the area 3, which is negative 6000 Newton to negative 875 Newton, and that is equal to negative 6875 Newton downward going to D. And at point D, there is a reaction load of 12,875 Newton. So, we will add that to negative 6,875 Newton, and that is equal to 6,000 Newton. Then lastly, 6,000 Newton plus negative 6,000 Newton is equal to 0. And that is now our shear diagram. As you can see in the shear diagram in span BC, there are unknown dimensions. So in small triangle, we will denote as an x, and for the bigger triangle is 3 minus x. And to compute that dimension by similar triangle, we have 5,925 all over 3 minus x is equal to 75 all over x. And by cross multiply, 5,925x is equal to 225 minus 75x. And by transposition, we will have an 5,925x plus 75x is equal to 225. And 6,000x is equal to 225. So the computed value of x is equal to 0.0375 meters. And by simply subtraction, 3 minus x is equal to 3 minus 0.0375 is equal to 2.9625 meter, and that is the dimension of the bigger triangle, and for the smaller triangle is 0.0375 meter.
Now that we are done with drawing our shear diagram, we can now proceed at step 2, which is to draw our moment diagram using shortcut method. But before that, we must find first the area of each segment in the shear diagram. Using the formula for triangle, A is equal to 1/2 base times height and area of a rectangle, which is length times width. For the first, A5, which is 600 multiplied by 1.5 is equal to negative 900 Newton meter. And for the next one, A6 is equal to 1/2 multiplied by negative 3,000 multiplied by 1.5 is equal to negative 2250 Newton meter. And for A7, 1 half multiplied by 5925 multiplied by 2.9625 is equal to 8776.41 Newton meter. And for A8, 1 half multiplied by negative 75 Newton multiplied by 0.0375 is equal to negative 1.41 Newton meter. For A9, negative 875 multiplied by 3, which is negative 2625 Newton meter. For A10, 1 half multiplied by negative 6000 multiplied by 3 is equal to negative 9000 Newton meter. And for the last one, A11, 1 half multiplied by 6000 multiplied by 2 is equal to 6000. Now we are done in calculating the area of each segment in the shear diagram. Now let us proceed in drawing the moment diagram using shortcut method. For M1, we will start at 0, line reference. For M2, we must add A5 plus A6, which is negative 900 plus negative 2250. The sum is negative 3150. As we can see, it is a negative, so we will going down from the line reference. Then for M3 is equal to negative 3150 plus A7, which is 8776.41. Then the answer is 5626.41 Newton meter. Will now going upward 5626.41. Then M4 is equal to 5626.41 plus A8. A8, which is negative 1.41. The sum is 5625 Newton meter. For M5, we must add 5625 and the sum of A9 plus A10, which is 5625 plus sum of negative 2625 and negative 9000, which is M5 is equal to negative 6000. And for the last one, M6 is equal to negative 6000 plus A11, which is negative 6000 plus 6000. Now we are going back at 0 line reference, and that's it. We draw the moment diagram using the shortcut method.